Hi, this is the presenter Rong Huang's speech of Article 3052. I come from Donghua University. The other authors come from National Institute of Informatics. Our topic is about security of facial forensic models against adversary attacks. First of all, about the research motivation. As we know, faces are silent information that directly reflects people's identity. Nowadays, non-professionals can easily manipulate the facial images by using these tools, deepfakes, the face-to-face, or face swap. It is virtually impossible to identify this one is a fake image by the naked eye. Recently, deep neural networks have shown outstanding performance in many computer vision tasks. Some researchers developed DNN-based models for image forgery forensics, MesoNet, forensic transfer, and Y-shaped network are three respective works. It seems that these DNN-based forgery forensic models are in charge of the security for facial images. Our question is whether these security-sensitive models themselves are secure if we consent the adversary. This slide lists what we do in this paper. For the Y-shaped network, we demonstrate the existence of individual and universal adversary perturbations. We use both the direction and the length of gradient to generate the individual adversary perturbations that can fabricate the classification and the segmentation results. We designed a new objective function that encourages the latent neurons to overfire without the need for training data. Then we examine the transferability across NC datasets and the NC models, including the MesoNet and the forensic transfer. Of course, the transferability belongs to the black box attack. 775 evaluators participate in our subjective assessment for evaluate the impossibility of the perturbations. Let me briefly introduce one of the target models, namely the Y-shaped network. It basically follows the autoencoder's structure but with two-pronged pathway, one for classification and the other one for segmentation at the end of the decoding network. In the middle layer, the latent neurons are grouped in two zooms. In the training phase, the upper zoom called 1 is activated for real image, while the bottom 0 zoom for fake images. Three losses, classification loss, segmentation loss, and the activation loss are used for training. By using the grading information of the activation loss, we can generate the individual adversary perturbations to fabricate the classification result. In this iterative formula, we should first prepare an adversary classification label that is opposite to the ground truth function. Here, C represents the resulting IAP, and the clip operation limited the perturbations magnitude. Not only the direction but also the length of the gradient is used here to ease the task of searching the adversary perturbations. As demonstrated in this table, for deepfakes dataset, only 10 iterations are enough to destroy a well-performed forgery forensic model. Interestingly, the IOU score, which evaluates the segmentation performance, decrease at the same time, even the segmentation loss is absent in this formula. We further discuss this phenomena in the next slide. In these examples, the top left tags stand for the resulting output of forgery forensic models. The bottom right ones are the ground truth classification labels. As we saw, the adversary perturbations not only flip the classification result but also fabricate consistent segmentation result. This is because the activation loss located at the middle of the Y-shaped network so that it affects the both classification and the segmentation results. Using the adversary perturbations, a attack can also mislead the forgery forensic models to output a designed segmentation result for fake images. To this end, he or she should prepare an adversary segmentation mask where the hair area instead of the facial area is highlighted as fake. In this case, the activation loss is still necessary and is combined with the segmentation loss. However, the adversary classification label is set to a value close to but less than 0.5 to loosen the interaction between the classification and the segmentation tasks. Let us turn to the universally adversary perturbations. This slide shows the overflying idea and the newly designed objective function. Without using the training data, we take a noise image as the network's input. We aim to update the noise image by searching some special patterns until it can overfly the design zone. In this example, after ending this UAP, the import images will overfly the neurons in the one zone, and these images must be classified as real. Here, A1 and A0 represent the sum of the activate integer for one zone and the zero zone respectively. However, it is a challenging issue to overfly the latent neurons for the autoencoder-based structure due to the small magnitude of the noise image. To overcome this problem, we design a new objective function consisting of an exponential term and a minus term. At the beginning of iterations, the difference between A1 and A0 is small because the import image is an initialized perturbation. Hence, we should set the parameter kappa to a value greater than 1 to amplify the difference. In doing so, the exponential term provides the source of loss to drive the gradient descent algorithm. After several iterations, the exponential term approaches 1. At this time, the minus term becomes a new driving force to further overfly the neurons. Note that if we exchange A1 and A0 in the exponential term and replace A1 with A0 in the minus term, the corresponding objective function can be used for overflying the zero. Here we show 6 universally adversary perturbations from which we can observe special textual patterns. The perturbations in the first row will overfly the zero zone, meaning that resulting output real is flipped to fake. On the contrary, fake images will be classified as real if ending the second row's perturbations. Here, columns indicate that the target models is trained on different datasets. Note that when generating the UAP, we do not need to know which dataset has been used in the training phase. We examine the transferability across NC datasets. The first row lists the original accuracy of forensic. The second row shows the performance degradation after ending general uniform random noise. We found the accuracy decreased by 88% from orange box to the blue box. This demonstrates the image agnostic property of the universally adversarial perturbations. Moreover, the UAP achieves larger accuracy drops than the uniform random noise, which validates the transferability across NC datasets. This table shows transferability across NC models. MethoNet and forensic transfer are included as target models in this experiment. The UAP generated from the Y-shaped network is used here to attack the two NC models, following the scenario of black box attack. On average, the UAP also outperform the uniform random noise, demonstrating the transferability across NC models. Finally, we introduce our subjective assessment. A pair of images were displayed on the screen. The left one is a clean image, while the right one is the to be evaluated image. Each evaluator was asked to rate the quality degradation for the right image by using 5-point opinion score. The higher the score, the better the vision quality. We have organized 755 evaluators online and followed these rules to conduct the subjective assessment. Please see more results at this website. We found that UAP achieves better imperturbability than IAP with a score close to that of clean images. Conclusion. We demonstrated the existence of IAP and UAP for the forgery forensic models. Also, transferability across NC dataset and NC models has been validated. This work provides a baseline for evaluating the adversarial security of new DNN-based forgery forensic models. Okay, thank you for your listening. Thank you for the platform of ICIP 2020, and thank you for all